So my name is Maxim Zavitsky. I am professor at the Department of Telecommunication and Radioelectronic System at the National Aviation University, and I'm going to talk about reliability analysis for radio equipment in the case of linear degradation of technical condition. So radio equipment is an integral part of the information support system in civil aviation. This equipment provides the following services: organization of communication between aircraft and controllers of air traffic control system, between personnel during the implementation of production processes, provision of civil aviation subject with navigation information, and radar surveillance, including weather condition at a specific airport. Ensuring the efficiency of the radio equipment usage for its functional purpose has a significant contribution to achieving a given level of air navigation service risks, safety, and regularity of flights. The operation process of aviation radio equipment is the longest stage of its life cycle. During this stage, intervals of infant mortality, normal functioning, and wear out are distinguished. The interval of wear out characterizes the beginning of approaching the limited time resources of the equipment. At the same time, the number of failures begins to increase due to the occurrence of degradation process in electronic and radio components, instability of power source, oxidation of contacts, and so on. The time moment of transition between the second and third interval must be detected in a timely and accurate manner to support the effectiveness of civil aviation tasks with the use of radio equipment. After detecting the degradation process, it is necessary to analyze the reliability of radio equipment and evaluate its residual resources. The task of degradation process detection and parameter estimation are related to data processing and decision-making systems. Data processing systems in civil aviation are provided with the collection, storage, and processing of data sets, characterizing the condition of the equipment and the components of its operational process. During processing, regression dependencies, classifiers, extrapolators, and estimators, and so on, are used. Advanced data processing systems, in particular for Industry 4.0, contain elements of artificial intelligence based on machine learning and deep learning. The degradation process can develop along different trajectories. The analysis of scientific research and the practices of radio equipment operation shows that the linear trend of the technical condition deterioration is justified in the vast majority. The analysis of degradation processes of radio equipment is usually performed on the basis of classical tools of mathematical statistics. At the same time, the task of detecting change points are solved by parametric and non-parametric methods, in particular based on the Neyman-Pearson approach, the Bayesian approach, the sign algorithm, the Wilcoxon test, and so on. In general, this problem is solved by testing statistical hypotheses. First of all, about the belonging of sample to one general population. Second one, about the occurrence of non-stationarity in the data trend, and about the type of probability distribution or the value of its parameters. So the task of evaluating reliability parameters are of reliability theory and mathematical statistics. The data processing technologies for this group of tasks include algorithms built on the basis of the maximum likelihood method, the method of moments, and quantile methods. In addition, both groups of problems can be solved based on the application of neural networks. However, their usage for reliability analysis is currently not widespread for reliability data monitoring due to the small sample sizes, which leads to training difficulties. The task of analyzing the deterioration of technical condition of aviation radio equipment are quite important from the point of view of operational efficiency. Untimely detection of deterioration not only worsens the level of light safety, but also leads to unnecessary costs for an increased number of repairs. This reduces the economic performance of aviation enterprise. Therefore, this paper considers the task of assessing the reliability of radio equipment in the case of linear trend of deterioration of technical condition. The paper aim is to synthesize and analyze the data processing algorithm for estimating the reliability of radio equipment based on the maximum likelihood method in case of linear degradation of technical condition. Let's consider the task of synthesizing the procedure for assessing the reliability of radio equipment. This procedure will consist of three steps. First, the detection of change point. Second, the estimation of change point parameters based on the maximum likelihood method. And third, the assessment of reliability parameters. As a reliability parameter in this research, the remaining useful life of radio equipment was chosen. The main limitation of this research for the specified problem are the following. First of all, the monitoring system measures the value of one defining parameter. The data are accumulated and collected in the corresponding data set with the size of n observations. The selected defining parameter has a direct impact on the occurrence of failure and misfunction of equipment. Second one, failures occurs when the defining parameter exceeds the operating threshold throw. Third one, the trend of defining parameters contain additive Gaussian noise with zero mean and standard deviation S. Fourth, the model of degradation of technical condition is linear. So the time moment, tau of change point occurrence is random. The second parameter of the model is the slope angle of the linear deterioration trend and its tangent d. According to introduced values, the model of the degradation process of defining parameter can be presented as follows. So the is value of defining parameter is initial value of this defining parameter plus tangent of inclination angle of degradation trend, the number of observation minus the time of change point occurrence, that multiplied by heaviside step function plus some normal noise. So we have here three random parameters. These parameters are d, tau, and I. So the first step of the process procedure is to identify the change point. For this, the simple hypothesis H0 of the absence of degradation is tested against the simple alternative H1 of its presence. Taking into account the probability density function of the values of defining parameters for corresponding hypothesis and alternative can be presented as follows. So we have here probability density function in case of deterioration absence. So we have only Gaussian noise with some initial value of defining parameters. And we have the probability density function for the case of alternative. So in this case, we have some mixture of our observed defining parameter. So the equations 2 and 3 can be used for obtaining decision rule based on the Neyman-Pearson approach. In this case, we can use the likelihood ratio or the logarithm of likelihood ratio. So we can write the following equation. So we have here logarithm of exponential function. After that, we have only the sum. So after mathematical transformation and simplification, equation 4 can be presented in the following form. So we have logarithm of likelihood ratio. It depends on some values of defining parameters, and this is part of this equation is some determined function because it does not contain random components, so we can calculated beforehand. So analysis of equation 5 makes it possible to proceed to decisive statistics. So in our case, we have very simple decisive statistic. So we need to find the sum of all the values of defining parameters, then multiplied by the number of observations. So the calculated value 6 should be compared with the decision threshold, which can be determined by the following equation. So we have here decision threshold. So this part of equation is obtained from equation 5, this from equation 5, and here we have the inverse Laplace function that depends on prior I determine the probability of false alarm. So if the value 6 exceeds the threshold 7, then a decision should be made about the presence of degradation process. Otherwise, the normal functioning of the radio equipment continues. The second step of the proposed procedure is the estimation of parameter D. For this purpose, the maximum likelihood method is used. So in this case, we can write the likelihood function in the following form. So before degradation, we have the product of probability density function that corresponds to hypothesis. And after degradation, we have product that corresponds to change point occurrence. So after making mathematical simplification, we obtain the following likelihood function. So all parameters except D in the equation 8 are known. So therefore, equation 8 must be differentiated concerning parameter D, and then we can get so that the derivative of likelihood function will be following, where constant L is some exponential function. So after that, we should equate this equation to 0. And to solve the following equation, so we neglect the factor L, and we neglect this part of equation, and we have only the sum. So we can present equation 9 in a more suitable way. So we find the sum of some sums, and we obtain 3 terms of sum. And our task is to find D. So this part of equation is known, these values are known. So we can find the equation 10 that will give us the estimate of unknown parameter D. So we can find it according to equation 11. So the resulting estimate is effective. At the same time, it should be noted that during its calculation, it is necessary to correctly determine the moment delta tau change points of degradation occurrence. This value can be taken as a point in time when the decision about the degradation process is made. Next, the monitoring system collects an additional dataset of a small size for the possibility of parameter D estimation. In this case, summation in formula 11 will be performed within the collected dataset. The data processing in the second step is enabled only after a decision has been made regarding the degradation of technical condition. The third step of proposed procedure is an assessment of remaining useful life for radio equipment. The estimation of remaining useful life of radio equipment is performed on the basis of degradation model 1 and the estimate 11. At the same time, taking into account the operating threshold, the moment of failure can be presented as follows according to equation 12. So this is the moment when our degradation begins. And we have here difference in value that divided by our estimate of inclination, our angle of degradation trend. So in this case, remaining useful life can be obtained as follows. And after that, when we put in equation 13 the estimate 11, we can get the final estimate for remaining useful life of our equipment. So this is equation number 14. So analysis of the detection procedure is performed by calculating the detection characteristic. In this studied case, the characteristic is the dependence of probability of correct detection on the value of degradation parameter. Using simple mathematical transformation, the formula for the detection characteristic can be obtained as follows, as it's shown in equation 15. Here you can see the figures that correspond to statistical simulation. In figure 1, we can see the different realization of defining parameters for different cases. So the green line corresponds the absence of degradation. So we have only observation for our parameter, and we should do nothing. So we have normal operation here. The black line corresponds to the occurrence of degradation. So we have here a small inclination angle, and when we use the data processing, for example, in sliding window, we can easily to detect this degradation, and we have much time to implement some preventive actions, for example, preventive maintenance, to eliminate the possible failure. And red lines corresponds to the great value of degradation process, so we can detect it easily, but we have much less time to implement some procedures, and in this case, the failure is still possible. So for generated datasets, we calculated the detection characteristic using statistical simulation and built the detection characteristic according to equation 15. So you can see here that results of statistical simulations that mentioned in this picture by dots coincides with the analytical equation obtained according to formula 15. Analysis shows that for the degradation parameter dz greater than 0.09, we can get the probability of correct detection more than 0.99. This feature proves the efficient and accurate detection of technical condition degradation. Figure 3 and 4 show the histograms of degradation parameter and rule estimates. It should be pointed out that for this simulation, the real value of degradation parameter was chosen equal to 1. The mean value of estimate is also equal to 1, and the standard deviation is equal to 0.017. So the type of distribution for the estimate tends to be normal. The estimate of remaining useful life can be also described using normal distribution. This can be proved using the theory of functional transformation of random variables. The mean value of the estimate is approximately 40 hours, and the standard deviation is 0.691 hours. So for the initial data set, this time is enough to carry out maintenance procedure to prevent possible failure. So conclusions. So the paper discusses the task of assessing the reliability of radio equipment in the case of linear model of technical condition degradation. The main attention is paid to the synthesis and analysis of data processing algorithm on the defining parameter of the equipment. The processing procedure includes 3 steps. First, the detection of change point. Second, the estimation of change point parameter based on the maximum likelihood method. And the assessment of reliability parameters. So the synthesis of each of the algorithm is performed analytically, and the analysis of first algorithm is performed analytically, and other algorithms are based on simulation. Further research will be aimed at improving the processing scheme, in particular in sliding window, and comparing it with the presented algorithm. In addition, it is planned to build a classifier of models of the degradation process for the possibility of adapting the processing and decision-making system to variable external conditions. That's all. Thank you for your attention.
Thank you for your report.
Yeah, thank you. So, any questions?
I have a question. May I ask?
Yes.
Okay, I have two questions. The first one is how to measure degradation of some elements. And the second one question is, for example, I have radar. Radar consists generally from such big blocks: transmitter, antenna, and receiver. If I go down, so the receiver consists of high frequency amplifier, mixture, low frequency amplifier, some detectors, analog to digital converter, some processor, computer. If I go more down, I will have, for example, in intermediate frequency amplifiers, I will have transistors, some power supply unit, and others. So the second question is, how deep should I take into account my elements for calculating probability of degradation?
Okay, thank you for your question. First of all, I should say that there are two types of degradation. First type of degradation can be considered in the high hierarchical level when we consider the whole system. So in this case, we can monitor the reliability parameters such as mean time between failure or failure rates. In this case, the main parameter of degradation will be or failure rate or mean time between failures. According to regulatory documents, the sign of degradation is decreasing in mean time between failure in 2 times compared with its initial value. So this research is associated to the second type of degradation when we have degradation in some defining parameter. So this type of measuring or study is associated with the lowest level of hierarchy. So here we consider the currents in some branches, the voltage in some points. We can measure the transmitter power, transmitter receiver sensitivity, and so on. So this case is associated with the electrical diagram of equipment. So in this case, we can talk about in general degradation, because we have, for example, not general degradation, but some degradation in one-time moment that can be that can cause to failure. So we, in this time, our degradation process, for example, if you see here for defining parameter, for example, here we see the voltages in some points. So in this case, we have increasing voltage, so it can cause to failure of some electrical component. So we have here the operating threshold, and we have here preventive threshold. Our task is to predict the time when our defining parameter approaches the operating threshold and to do some preventive actions to eliminate possible failure and eliminate the process of degradation. So, two types of degradation. First type for the highest hierarchical level, and this type in this research for the lowest hierarchical level.
Okay, thank you very much. I don't have questions.